Hey, what's going on, everybody? It's your boy, AlgeBruh, coming to you live and direct from the studio, aka my living room. About to talk to you about geometric sequences real quick. So the basic idea is that we're taking an arithmetic sequence and going to change that key factor that made it arithmetic. So let me give you an example of that real quick before we get started. Being 4, 6, 10, blank, blank, blank. This is how we started at the beginning of the chapter. We said, you have been doing this for a long time. You recognize patterns pretty quickly, pretty easily. You figured out that it's plus 2. And I'm not telling you anything that you don't already know. Filling in these different spaces is pretty straightforward and easy for you as well. However, what the important thing for you to notice right now is that this pattern that you use is plus. This is an arithmetic sequence because it is plus. No matter what, when we're talking about arithmetic things, it is regarding plus or minus that same common difference. So if I'm not going to talk about an arithmetic, I can't talk about plus or minus anymore. That leaves you with two options, times or divided by. So if I give you a second sequence, very similarly, 5, 10, 20, 40, blank, 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 I want to know what's the relationship. Look at it, you get it, you see it, it's not hard. You tell me that it's supposed to be times 2 every time. So filling in the next space, you're just going to multiply times 2, and then you're going to do it again, and then you're going to do it another time. So this type of problem is not an arithmetic sequence. It is what we call a geometric, like geometry, like when we're talking about shapes and fractals and tessellations. It's where you're taking the same picture and multiplying it over and over and over again. A geometric sequence is a list of numbers following a multiplication or division pattern. We're still going to have all the same characteristics otherwise. We will eventually talk about making them into a series. We'll talk about what it means to skip a level, and we'll talk about what it means to go down as opposed to getting bigger. So geometric sequence is the big deal, however, is instead of plus or minus, we're now talking about times divided by. First example of the day. I want to know what it is that makes this a geometric sequence instead. It's a geometric sequence because it is times 2. Instead of calling it a common difference, we're going to call it a common ratio. It is the number that you're using to multiply. But just like we talked about in an arithmetic sequence, it has to be between consecutive terms. The consecutive terms meaning it is between term 1 and term 2. I can't skip it all if I'm going to be talking about a common ratio. Whenever we talk about a common ratio, we're using the letter R. So what is the common ratio between the numbers in this series? that would be a ratio of 5 between the numbers in a series or sequence that's going down. Most people would say it's divided by 2, but instead we want to talk about what it means if you're multiplying. This is going to be r is 1/2. It gets half the size. Okay? So if you look at a problem and you see a division pattern, just flip it over. And then I'll give you a particularly interesting ratio to me personally. I'll start you off with a 6 and say it goes to negative 12 and then back to positive 24 and then it goes to negative 48. How do you feel about that? Somebody's going to yell out that it's supposed to be a common ratio that is a negative number. So we can have a fraction, we can have negatives, but we're looking to see what the relationship is that is repeated. Like I said earlier, one of the things that I really want to know about is what happens if I decide to skip a term. So this is the sequence that I want to work with for the next couple minutes. I gave you a relationship. You can see it in the first 2 terms, but I don't want to look at that right now. I'm going to hold that off for later. Just ignore the fact that it says 4. I need some type of relationship that exists between these 2 transitions that is going to be repeated. This common ratio that I'm referring to right now, that wouldn't be too hard to jump space. The relationship going from 12 all the way to 108 is r times r squared. So I want to know then, if I'm multiplying r times r, how do I figure out what's that r squared equal to? Well, the rule is you just divide. R squared equals 108 divided by 12, which means that it also equals 9, and R equals 3. So the common ratio, what I'm multiplying by every single time, is not coming from some particular addition problem. It's got to be repeating multiplication or repeating division, and when you do that, you end up with exponents. Now you see why we did logs first. It's because we're going to be dealing with exponents. The pattern that I gave you is still the same pattern as if I had given you that 4 in the beginning. 4 times 3 is 12, times 3 gives me 36, times 3 gives me 108. And the goal is, no matter how many spaces I skip, I'm just going to be using that as an exponent. The numbers this time, 13, blank, blank, blank. And then I'm going to go with feeling like it's going to be pretty interesting if I multiply it and I have, I don't know, 26 here. So that's a problem where you see that it's times 2. This relationship goes times 2, but there's a bunch of tiny, smaller relationships that happen in between there. I go from the first to the second, from the second to the third, from the third to the fourth, and then finally I get to the 5th term. My first term going to my fifth term gave me four iterations of the same common ratio. R to the fourth equals 2. Actually, our common ratio this time is a radical, the fourth root of 2. Now, I don't intend on giving you too many fourth root problems that aren't going to work their way back out, but you need to understand all I'm telling you to do is multiply that every time. And thus we move on. If I'm telling you all this information, I'm comparing it to an arithmetic sequence over and over and over again. The big thing you need to understand is that just like an arithmetic sequence, there's a shortcut to figuring this information out. The formula for the term of a geometric sequence is a sub n equals my first term, that's my initial condition. The relationship is through multiplication, so I'm going to be multiplying using a common ratio to the n minus 1 time. Meaning, I start at the first term, use a common ratio over and over and over again, but I did an initial condition. I want to know, what is the n term? Defined by a sub 6 equals 14, and a sub 9 equals 112. So quickly, what that means is that my sixth term, way down here, is 14. I don't know the seventh, the eighth, but I do know the ninth. First things first, we always, always, always need to know what is the value that is being used. It's 3 iterations, and 9 minus 6 equals 3 iterations, which means that R is the value of 112 over 14. R equals 8. So now I know what R is. I can trace my way backwards to find a sub 1, or I can think about this algebraically. Since I know what a sub 6 is, I can plug it in. I don't know a sub 1, but now I know the common ratio, and I know that n is 6. This relationship, this formula, can take you directly to your a sub 1 value without actually having to worry about the calculations. Your calculator is a magnificent machine. Use it for that purpose. Use it because it's a magnificent machine. think I've got time to do one more sequence for today. I'm not going to try to overcomplicate things right now. I want to know what it is. A sub 2 is 14. No. I did 14 last time. Let's do A sub 2 is negative 15. And A sub 7 is a positive 408. So our thoughts, first of all, need to understand what are we going to be getting from R. We're not changing one particular place. We're jumping 5 places this time. So R to the 5th equals 480 over negative 15. I can send that into a, oh wait, that reduces R to the 5th equals 32, which makes R simply 2. Actually, I just realized I need to take a backtrack. I forgot to do the cube root of 8 when we had a problem. R is not 8. R is 2. I was wondering why that thing came out so ugly. Get rid of all that. It should be over 32 instead. See? You guys are supposed to be the smart ones. You guys are supposed to be catching these mistakes. Final answer instead. Much better. So, now we come back to the present. The nth term, I have R equals 2. I want to know what is the formula that I should have. So let's say A sub n equals initial condition times 2 to the n minus 1. And this time it's actually a whole lot easier. I can just trace it back by dividing by 2 instead. A sub n equals negative 15 halves times 2 to the n minus 1. Homework tonight, page 936, 1% R, page 937, 2 through 20 even. It's a 2-page homework assignment. Not that bad. I believe that you can handle it. Just don't make the same mistake that I did in the video a minute ago, forgetting to do the cube root or the 5th root or whatever root you need to do. I'll be back on Monday. See you.